Okay, so I think everyone's back, or at least everyone who matters. So let's, it's 2 now. Or it's after 2. Let's continue on where we left off. So before lunch, I started telling you about polymorphism. And, well, we kind of got partway through the story, because I talked a lot about types, which is kind of the point of polymorphism. I'm really adding a feature that's about types, but I didn't tell you how to run these things, or on the other hand, how these things impact running. So to start, I'm going to give the operational semantics, so the dynamics of this language system F. Added some new stuff, so we sort of talk about how do you evaluate the programs of system F that's got types, type annotations, type specialization all over the place. How do you accommodate that? And then, well, I think the punchline is that all of that doesn't matter, right? And so that's the property we'll look at, which is type erasure, which is here everything's very explicitly typed, and we're only talking about programs that are well typed. But I don't really want to have types running around when I run a program. They're not really helping the computer. To the computer, everything's just bits anyway. So why am I doing all this extra work? So erasure is, it doesn't matter. It's just for the benefit of a person, and it's in the mind of a person or in the mind of the compiler, but it's not in the mind of the machine. That's what erasure is. Okay, so and I think these things, like system F is kind of deceptively simple, which is you ask, how do you do type specialization, and what are all of these things? And the answer is, they're just like functions. It does the same things, right? It's substitution and application. Really, the operations are the same. So it's kind of like that miracle that really, from understanding the lambda calculus, we kind of had all what we needed to understand polymorphism too. We just have to lift that to the type level. That's the only trick. Okay, so let me write down the operational semantics. So I'll show both the call by name and call by value versions, because it does have an impact a little bit when it comes to erasure. So we'll look at both of them. So the call by name version of system F, and I'll do the call by name version because that was the first version. Call by name, right? So what do we have to do? Well, we've got to say what the end states are, right? That's the values is what we've been calling them. What do I expect to be the result of running a program? What are the basic reduction rules? And then how do I find them? Those are kind of those 3 basic ingredients of doing one of these operational semantics. Is where am I going? How do I get there? And how do I do that? How do I make progress? Okay. So what are the values? So this is kind of like with the lambda calculus, right? So what were the values of the lambda calculus? So lambdas are values, right? So a lambda x dot tau dot e, or x colon tau dot e, is a value, right? And let's see, is there anything else that should be a value? What was that? Variable? Yeah, sure. I'll accept a variable as a value because those won't be different things. Some people argue and say that's impossible. So here's an open value. So this is what Plotkin defined the call by value lambda calculus to be, right? These 2 things are values, so that's going to be the values. Is there anything else, though? What else might be? Big lambda? Right? So that's also a lambda, right? So should that be a value? And maybe you'll say no. Yes, and I'm going to say yes, because big lambdas are just like little lambdas. They're just over types. So I'll say those are all values. Okay? So those are values. And you might say, I don't want a variable to be a value, and that's a choice you could make. That's fine. That's where we're going. Now, what do we do? And I always find it easiest to start with the main rules of what's going on, and then we can talk about the issue of how to find where to apply those rules later. So, well, I've got the lambda calculus. So what was the main reduction rule of the lambda calculus? What was the main driver? It was the beta law. Right, and what did that look like? That's if I had a lambda, which is a function, applied to something, you substitute. Right? So that rule looks like lambda x colon tau dot e applied to some e prime takes a step to e with e prime for x. Right? So that's a step I could take. And to be clear, right, so in terms of the inference rules, that's an axiom. Usually people leave off that top line. They just say axioms, which means the same thing. Okay? Is that it? Do I need any other rules? Right? Probably, right? So how do I resolve the polymorphism bits? Because that actually shows up in the program. What happens when I say, here's the polymorphic identity function, and I want to use it on a number, and in particular, the number 1. Right? So here, I could have the, remember the polymorphic identity function said, for any type alpha, I'm a function from alpha to alpha, which you would write that term as, right, big lambda alpha, and let me bring down the typing rules. I'm kind of, right now I'm just following the type at this point to write the program. I've got a for all. What's the only way to get a lambda? So essentially, introduce the name in the type into the program. Now, okay, I've got an arrow. What's the only way I can really get an arrow or introduce an arrow? It's with that rule. So I now have a lambda, and that's got an argument, an x, and what's the type of that argument? It's got to be an alpha because that's what it says here. And so now I'm in the body of the function, and I've got to return some sort of alpha. And what do I do? Well, isn't it convenient that I have one? It's kind of the only thing I can think off the top of my head to do. And in fact, it is the only thing you can do, which is return that x. Right? So that is the identity function, the polymorphic identity function. But when I go to use it, I have to say, what type do I want to use it at? Right? So I can't just say identity applied to something. I have to say identity specialized to numbers. And then I have a function from numbers to numbers. Right? So this has the type num to num. Why do I know that? That's just this rule. Tau is alpha arrow alpha. Tau prime is num. And, where did I write that up here? Alpha arrow alpha with num for alpha is equal to num arrow num. That's just the definition of substitution, right? It's not really any different than distributing over a product. So here, now I've got a num to num. Now I can pass in a number like 1. And then this whole thing is a number, right? Because when I apply a function to an argument, I get the type of the result back. And, well, intuitively, this should evaluate to 1 because, right, that's what the identity function does. It just parrots back what you gave to it. But you've got this thing in the way, right? So the function application rule doesn't apply because this isn't a function application. This is a type specialization. So how do you resolve that? Right? So what's the case for there is what if I've got, right? So ID is a big lambda, and this is a type application. So what happens if I've got a big lambda and a type application? What do I do there? Do I get stuck or do I do something? I should probably do something. What should I do? Any guesses? Yeah? You could. So, okay, so this was the suggestion. So this is a good. I could say that. I did something at least, and I've made progress, and it's more or less kind of what you want, but is there a comment or a other suggestion?
Yeah, so you have to substitute in tau for alpha.
Substitute in tau for alpha. So let's compare these two things. So right now, I'm in that definition part where I'm saying what it is, and technically I can't be wrong because what I say goes. The difference is you want to ask, what are the consequences of your definitions? What are the properties you get back? That's what you actually care about, is not the definition, but what's the results. So one suggestion was just return E, and the other suggestion was you should plug in tau for alpha, right? And yeah, so which is the right one? Huh? What was that? So plug in tau for alpha. So, well, the question we can ask is why, or what's the difference? So what happens if I don't plug in tau for alpha? And what will happen is, remember we had the type safety, well, really lemmas. So this is a good point to sort of say. Right, there is the progress and preservation lemmas. So what are those? So I'll say lemma, progress. Right, so just to, in general, repeat what the were. So progress says that if progress, so if I've got, and here I'll say like this, okay, if I've got, no, I was using a bullet, so a term or an expression with no free variables, value variables, but maybe some free type variables, maybe those are okay, because a well-typed expression, but it's got no x and y free in it, then either E is a value or E steps to E prime for some E prime. For some E prime. Right? So if it's well typed, it's either done or it can do something. Right? That's progress. Preservation says that things which are well typed stay well typed when they move around. Preservation. Okay, and by the way, when I say this, what I really mean is derivable. Right? So this is kind of implicit. We coerce between the judgment itself and saying, I've got a derivation that ends with that judgment. So I forgot to write that. But most properly, I should say, if I've got a derivation of this that ends with that judgment, then this property holds. Right? So that's what that means. So preservation. What's preservation? That said, right, so if I've got something well typed, so if theta, gamma, E has type tau is derivable, and E takes a step to E prime, then theta, gamma, arrow, E prime, tau is derivable, right? So if something has a type and it takes a step, then the thing it steps to has that same type. Okay, so that was preservation. And so it's really common for people to say that this is type safety, which is not exactly accurate. So this is an extremely great way of proving type safety. So if you have progress and preservation, for sure you've got type safety. But type safety is kind of a bigger step sort of property in general. So type safety theorem, type safety, says that if theta, well, and this is for system F, so I've got theta, so it changes slightly depending on what your judgment is, but if I've got a well-typed something, right, so if E is well-typed, so is derivable, and E takes many steps to E prime, then E prime is not stuck. And quickly, what stuck means is that I'm not a value, but I cannot take a step. Right? So if I've got something which isn't a final state, but has no transition, that's something that's stuck. And so that extremely common case would be something like, I've got f applied to 1, I've got no definition for f. What is that step to? Nothing. Is that a final state? Not really. So that's stuck, right? So that was the free variable case of a type safety problem. But a more serious one as well is, what if I instead apply, let's say, the string hello to 1. That's even worse. It's not just that I forgot to define something, but I'm calling a string. So I'm jumping to somewhere where the string is, and that sounds like a pretty serious memory error that could corrupt my program if I wasn't careful in checking for these things. So that's really bad, right? So those are is that if you're well-typed, no matter how many steps you take, you won't get stuck. So this is kind of that original motto, which was well-typed programs don't go wrong. Go wrong here, I'm saying, is be stuck, right, is how we're modeling it. And what was that? E prime is not stuck, right? So if I have, well, yeah, so that's the, no matter how many steps I take, I don't get stuck, right? So I can, either I'm a result, or I can keep taking more steps. And, okay, well, clearly this is just a combination of those two, right? If I start well-typed, then I use preservation to say that E prime is well-typed at the same type, and therefore it must either be a value or take a step, and therefore cannot be stuck, right? So this is a really great way to break down this type safety problem. But it's possible to have a language that is type safe, but doesn't have preservation, or yeah, especially preservation. Usually progress will be an issue, but you might not have preservation. And that's actually a serious thing. So you might have type-safe languages that don't preserve types. And, well, that's not wrong, it's just more complicated, but there might be a reason for doing that. But that's kind of the issue here. If you do this, you've got preservation, right? That's something you should prove essentially, which is if E, so intuitively, if E is well-typed, then it's got an alpha in scope because it's under a binder for the big lambda, and there's a similar substitution lemma, which says, if I'm an expression that has a free type variable in scope, and I have a particular type tau, then you can plug in any type you want for that alpha, and that's also well-typed as long as you substitute everywhere for that alpha, right? Because alpha might appear everywhere. It might appear in the resulting type and also in the gamma. So this is another substitution lemma you'd want, just like the one we saw much earlier on. So this is type substitution. Type substitution. Right, and that looks something like if theta with an alpha and then a gamma entails that E has type tau, and theta entails that tau prime is a type with only theta in scope. So if both of those are derivable, then so is theta and gamma. Whoops. Let me check. So this is let's leave some room, theta, gamma, e, and tau. And the question is, where might this alpha occur? Right? So I'm plugging in for the alpha in e, but alpha might be mentioned in tau, right? And alpha might be mentioned in gamma. It's just sort of a free variable that might appear anywhere, right? So the substitution lemma is more interesting because you're plugging that tau prime in everywhere. So here I just mean like plug in for all of the types that are describing variables in gamma, right? For each gamma of type tau double prime, plug tau prime in for it. So it's like a by pointwise definition. It's kind of tedious to say, right? And so this is tau prime for alpha, right? And so here the idea of, gamma, if I've got a bunch of x of type tau 1, xn of type tau n. If I want to plug in tau prime for alpha, that means just plug it in at all of these places. So that's going to look like x1 with tau 1 with tau prime for alpha, xn, right? So that just means just do that everywhere. Yeah, question?
So it's fair to say that big lambda is analogous to
Yes.
Is it possible to build omega in the equivalent of omega big lambda? Or is that
When you say omega equivalent to big lambda, what does that mean?
omega built out of big lambda? So analogous to the omega.
Oh. Yes. So the thing that loops forever, right? Could you somehow, if there were not typing rules, right? If I just let you write anything, right? Because omega kind of didn't work for types. Without type checking, you can't do that with a big lambda because the culprit was x applied to x. And the thing a big lambda abstracts over is a type, alpha, and types can only appear as arguments. I can't say that a term or type is a expression, right? So I can't just say alpha applied to alpha, so I can't do the same thing, right? So just syntactically, before we even look at typing, I syntactically cannot use the big lambda to make an infinite loop or any other sort of loop. Correct. And that is because of the way I defined it, where all sorts of things are expressions, and I can apply any expression to any other expression. But types themselves are not expressions. They only appear here in a specialization as an argument of a big lambda, or also here as an annotation that doesn't really have any role in reducing. Why not? Because when I see a function, the reduction of a function, this tau is totally pointless. Right? I'm not checking anything about tau to see what to do or whether or not I do this. I just throw away the type annotation of that parameter and do the substitution and hope it works, right? The idea is that the type checker statically checks the property, and if it's well typed, we say, yes, it has it, and now I can completely ignore the problem when running a program. Right? So there's no dynamic type checking at runtime going on. So this one you might as well not write. It's just for the purpose of knowing what the type of a function is, because otherwise it might be hard to guess tau. It's just for the benefit of the type checker. Great. Okay. So that's the difference here. So in this rule, when I plug in tau for alpha, the reason you'd want to do that is because that's what a type specialization looks like. When I have some generic thing applied to a type, that's the type I get out. So if I plug in tau for e by the substitution lemma, it has that same type. But if I don't, it wouldn't have that same type. So I wouldn't have preservation. But I'd still have type safety. That's something you could prove. But you wouldn't have preservation. And it's nice to have preservation, so if you can have it, you probably want it. Unless you have a great reason not to. But I don't see why that is here. So, again, definitions aren't wrong, but this is probably the better one because of how it impacts type safety. Was there a question or no? Okay. Oh, yeah.
What is replacing tau prime by alpha in gamma and e? That
So the substitution lemma here is generally, I want to plug in something into E. So if I plug in 5 for x and E, none of the types change. But if I'm specializing in alpha, that same alpha is appearing all over the place. And so I should plug in everywhere, right? So that's kind of the idea. If I've got a generic library and I now specialize and say, it's not a set of anything, it's a set of numbers, I should instantiate the types of all of those operations to also be talking about numbers and not generic things.
The gamma and E should be referring to tau instead of alpha directly, right?
So the alpha here appears all over the place to the right. If you plug in somewhere, you should plug in everywhere, and that's the lesson. Yeah. So this is the definition I will choose because it has better properties. So getting back to that, I would rather have safety or have. So I'm going to do that one. That's the reason why that is the chosen. So those rules, and then what's the last bit on finding out where to reduce. And so where do we reduce? So I'll start by just summing it up with the evaluation context, which, well, I always just reduce an expression. Where else might I have to? Right? So remember what we had for the lambda calculus. If I see an application, I might have to reduce the function part. Right? Is there anywhere else I kind of have to dig into to find where the real work is? Any guesses?
I just want to have a review of what they use.
Yes. So I'm defining contexts, which is some terms, but there's a box somewhere in it. And the box is describing where I want to reduce. So here, I would like to reduce here, so let me put a box around that, and I'm describing where the box goes. So this box, if the E is just box, that means I'm reducing the whole expression. But maybe I don't have to reduce, I don't have to step the whole expression. Maybe the step is somewhere inside. So that's what the rest of them do. So this is the case of, what if I could take a step in the function? Well, it's okay, that's the place where you might want. And so this rule is just these rules. That's what this box signifies. This one is that if I've got, if E takes a step to E prime, then E applied to E1 takes a step to E prime applied to E1. Right, so that's what this case signifies. It's that. Any other place I should have to evaluate inside a sub-expression and not just the whole expression. So there's another type of application, right? Is that what you were going to say? Yeah, so there's that application too. What if I've got this, and this is not a big lambda? Then this rule doesn't apply, and oops, I'm stuck. Right? So you should also evaluate the operator side of the other kind of application, which then says that this is also another form, and that means I've got this rule, which is that E steps to E prime, assuming that E instantiated at tau, assuming that E steps to E prime, then E instantiated at tau steps to E prime instantiated at tau. Right, so this is the, what are the real steps? That's the real work and the interesting part, and this is just a detail on how to find those steps. Okay? Yeah? So, yeah, you could, so in general, usually the way I define things when I'm defining dynamics is I don't bother saying everything's got to be closed, right? But you're not going to have properties like type safety unless they are. So the kind of suggestion here is it doesn't matter if you have type variables for progress, right? That's the main, I don't get stuck, I can do something. And why is that? Intuitively, why would it be okay to have, oh sorry, that's not type safety, this one is type safety. Why is it okay, why can't I get stuck if I've got a free type variable in scope. Why is that? What's the grammar? That's a value, that's a value, that can't happen, right? Why not? Because I don't allow any free regular variables in my program. So here, either E1's a lambda, right? It could be a value, in which case it's a lambda and not one of those x things because it can't be a variable. Or it could take be an x, I would get stuck. That's sort of the problem you want to stomp out there, that if E1 here is x, then I can... but what about this? Well, it's well typed, so it can't be something weird like a lambda or a number, right? So it's got to be a well typed thing. So if it's one of these things, that's okay. If it's some other application thing, well, that makes progress by the inductive hypothesis. Or could this be an alpha? Well, no, that's got to be an expression, which could be a variable, but I'm ruling that out. So the question is, can an alpha ever appear in an important place where that's really the driver of my decisions, right? And the answer is no, because of the way I define the syntax. So in that sense, really the alphas just kind of move around, but they won't matter. And that's kind of to do with type erasure, which is I never really need to know what they were in the first place. So you have type safety even if you've got alphas in scope. And that could be a really useful thing, as I kind of alluded to, which is mentioning a type that I haven't defined what it is, which maybe I'll import from some standard primitive library of primitives. But I could still run the program without having those types. Right, that's the kind of thing. Huh? So the point is, and this is kind of that goes along with erasure that I'll get to in a bit, which is when I run it, I erase it all anyway. So once you've erased, I've scrubbed out all the types, so it didn't matter if there was some to begin with, because I'm just forcefully getting rid of them. Right? So in terms of what's the minimum I need to get type safety or to get progress, well, I can't have free regular variables x, y, and z, because I clearly can come up with counterexamples in which I'm stuck. But I can't come up with a counterexample for a type variable that gets me stuck. So I could say this has got to be empty too and also be true, but that's just weaker than this one. Okay? I'm kind of saying what you can get away with, right? We're trying to, get away with as much as possible without getting caught. That's, in general, a useful thing to do. Okay, and then so this is called by name. Is there any sort of other questions about type safety? So I'm not going to go through the proof, but how would you prove progress? Right? We kind of saw how to. Well, did we do the proof of progress or show a case? Maybe not. I think we did preservation. No, maybe we did progress. But progress, you kind of just go by. You check what are the typing derivations I could have and what kind of reductions I could do. You go by induction on that, and then you just sort of show that I don't get stuck. Where the fact that I don't have bogus things in the wrong places because it's well typed, and the fact that I don't have free variables rules out all of those cases that I don't know what to do. Or I'm a value, and then I have nothing to do. And then preservation uses that extra substitution lemma in this case, right? So these just kind of follow directly by an inductive hypothesis, right? We'll assume that I have preservation here. It's got the same type, so I can put together a modified subproof. But this is the main thing where stuff is changing, right? So to check that this has the same type, you'd have to make sure that substitution makes sense. And we kind of saw that lemma before. Substitution is a sensible operation on typing derivations. And because I have another sort of variable to deal with, I've got another sort of substitution to deal with. And that's what's going on here. The reason why this preserves types is because substitution makes sense. Oop, it's underneath. Substitution makes sense. That's kind of like that heart of preservation. And you're just doing an induction on what you might do. Okay, all right. So this is the call by name calculus. And that was the first one, so I did that one first. And I'll do the other one, call by value calculus, because they're both really useful because system F shows up all over the place when studying programming languages, because in practice, if you have types, you want polymorphism as just a reasonable language feature. So it kind of is the workhorse where you're just constantly, if you want to know how to work. Whether or not you're working with a lazy or a strict language, it depends on whether or not you do the call by value or call by name version. Okay, and so what changes do we have to make for call by value? Right, what changes? So, what about the definition of value? Do I really need to change that? Not really. That kind of was the same. Well, at least this part was the same for the simply typed lambda calculus, so it shouldn't be surprising that big lambdas are about the same thing, because they're both some sort of lambda, and they kind of work the same. So the definition of value is the same. What other rules do you get? So, well, the main thing, right, the point of what makes it call by value is that I'm restricting what I'm substituting during a function call, right? So that main rule was that if I've got lambda x of type tau and e applied to e prime, I'm allowed to step that to e with e prime for x only when e prime, right? That's the only time I'm actually allowed to do this. And so that was just from the lambda calculus. What about for the polymorphism? Does anything really change there with that, right? So the rule I had was big lambda, alpha dot e, applied to some tau, takes a step to e with tau for alpha. And what, I guess, does tau have to be a value? Is that a thing that really makes sense? Can tau have a value? Not really. So that actually just doesn't even change at all, right? So the call by value system F is really just the call by value lambda calculus and plus the exact same extension for handling polymorphism, right? So the polymorphism, at least for running programs, doesn't even change what you're doing there, right? Okay, so what else, right? So what were those extra rules for finding where to reduce? It could be that I need to E1, E2. Maybe I need to reduce an E1, right? That goes to E1 prime, E2. If E1 goes to E1 prime, right? Maybe I have to reduce in the other place. E1, E2 goes to E1, E2 prime, assuming E1 is a value, and E2 goes to E2 prime, right? This was just the lambda calculus. And then the same thing for polymorphism, right? Because I don't evaluate types. What would that mean? It doesn't really mean anything in this language, at least. What evaluating a type is just one of those things. There's no reductions to do, so I just evaluate in the function part, or in the operator part, in the generic program. E1 prime tau, if E goes to E prime. Okay, so then that's call by value, which is to say, for defining what to do, it only matters for the parts that have to do with just regular old functions. Right, so that's kind of the story we already saw before. So that's the two semantics. Are there any questions about those? Hopefully that's kind of clear on what's going on. Polymorphism does kind of surprisingly little in the running of programs, perhaps. Maybe you'd expect something more exciting, but it almost is boring how little what's going on. Yep? So if I'm specializing a generic program, if I don't know what the generic program is, run it.
So wouldn't we first specialize and then run it instead of partially
Well, so I don't have a generic program yet. E is an expression that if you were to evaluate it would hand you some generic algorithm. I do not have one yet. I would like to get one so that I could specialize. This is specialization. If it doesn't look like a big lambda, I've got nothing to specialize. I've got nowhere to plug that in, right? So I can't specialize some big loop.
What would yield a big lambda expression?
So I could have, well, I'll write it this way, somewhat artificially, but that's okay. So here is another program I could write. So what about a function which takes 2 arguments and returns one of them? Right, so what if I have lambda x and lambda y, and then I return x? So what's the type of that intuitively? Well, it's give me an alpha and beta. I'll return you an alpha. And there's for alls in there somehow. Right? So it's really for any alpha and any beta. And so I could say is a type because I've constructed it with arrows and for all. Is a type. And so how do I match up the big lambdas here? I would have big lambda alpha. X has type alpha. Oh dear, I ran out of room there. Big lambda beta. Lambda y of type beta. X. So this term has that type. And I'll call this const. Right? Because when you call it with one thing, it's the function that always returns that thing. And I could say const, let's say num, and I'll give it a 5, and then bool, I will give it true. Right? And so this will hand me back some generic thing, but it's not a big lambda. Right? So I have to evaluate it to get that big lambda. In the same way, you have partial application, and you might have to evaluate something until I find And so that's where we get erasure. And the idea of erasure is, can I take a system F term and scrub out all the types, and then I just get an untyped Lambda-Calculus term. So it won't be simply typed because system F is much more expressive than the simply typed Lambda-Calculus. But at least it will be a Lambda-Calculus term because I'll just have lambdas and applications. Once I scrub out everything else, once I take out that line, it's just Lambda-Calculus stuff. So let's look at erasure. So first I will define what erasure is formally. I've just sort of described what I want to do. So, erasure, I'll just say erase, and you just define it by induction on the expression, because erase is some operation in the meta syntax or the meta language where we are manipulating expressions that will take an expression of system F and return an expression of the Lambda-Calculus. Okay, so erase x is x, and the idea here is you just preserve Lambda-Calculus stuff and you throw everything else away. Right, so if I erase x, I just get x back. X, if I erase, I could have a lambda. And actually, to make this quite explicit, I'll even erase the dynamic because I don't need it. It had nothing to do with dynamics. So why even bother writing it anymore? I'm really trying to get into the untyped Lambda-Calculus, which has no mentions of types in it whatsoever. So there, I'll just say lambda x dot erase E. Right, so you have to erase the body of the lambda, but I've gotten rid of the type annotation. Erase an application E1 looks like erase E1 applied to erase E2. What else could I have? I could have big lambda and type instantiation. So those, right, so erase a big lambda alpha dot E will look like erase of E of a type specialization just looks like the erase of the generic thing because we don't care what types are. So that's erasure. That's a formal definition of what erasure is, which is take an explicitly typed program and rub out all the types. Okay? And the idea that erasure doesn't change the result of a program, right? So I would like to get the same result as if I still had my original program that I had written. I just don't want to have types coming up my runtime system if they don't do anything for me. So the theorem here, the way I've stated it, theorem for type erasure, says that if E reduces to some value V, right, so V is a result, then erase of E erase of E goes to erase of V, right? And so that's what I would like to be, right? So the idea is if I erase a program, do I get the same result? So the question is that true? I'm seeing at least some confused looks. So what might go wrong? Is there a counterexample? Is there a counterexample? Can we see something where it might go wrong? So, there's the first one is which semantics do I mean? Because I define both call by name and call by value. And we can ask, does that make a difference for this kind of property? So for example, it does not make a difference for type safety, right? No matter which of the two I pick, I've got type safety. Both notions of arrow are type safe, or both notions of evaluation are type safe. So is there an impact there? So yeah?
So big lambda is a value, right?
So number one, big lambda is a value. So where can that mess me up? Right? So, this was call by value. I want to do call by name first. Call by name. What happens if I stopped because I got a big value, or big lambda, as my value, and I then erase it, which means I keep running? Oops, that might not be the same thing, right? Because in some sense, this big lambda hid some steps I should have done and I stopped too early. So how do we fix this for call by name, this specific semantics? Because a theorem like that, really the maps to is for a specific definition like call by name. Right, so how do we fix that? What's the problem? And really, if I'm going to erase polymorphism and big lambdas, then I shouldn't be running a program that's intended to return a big lambda, because I'm erasing that type, so that doesn't really make sense. So I'll say here's the fix for call by name, which says you should only really run programs of certain types And so this is kind of a general thing where there's maybe a behavior you don't want to see, which is I saw that you returned a big lambda, and I'd rather just get rid of big lambdas. So I shouldn't try to look at a big lambda in the first place. So the fix for call by name, so the CBN fix is you add an extra premise, which is, well, not if, but if E is some type that's not a for all. Tau and tau is not equal to for all alpha tau prime, for some tau prime, right? So I can't look at something that's a for all because then I would see a big lambda, and erasure changes what I do because it tells me when I stop, if I've hit a big lambda or not. Is there any sort of confusion there on what the counterexample is? I mean, the basic counterexample is alpha dot, let's say for now, lambda x dot x applied to, that's a value, right? So it reduces just to itself, right? That is the value it reduces to. But when I erase it, then I get applied to lambda x dot x, and that's not a value, and it would take a step, right? So I do something different. I don't want to know the difference, and really I don't care because I shouldn't be trying to run a program of that type anyway. Okay? Does that make sense? So if you're going to erase for alls, you shouldn't look at for alls. Okay, that's number one. Is there another problem? So this is kind of like a detail because usually a program is like a number or a string or a combination of a string and a number if it's like the output of a console program and an error code, right? So usually you're doing something concrete like that. And that's kind of implied right here, right? If I've got a program, and it make a difference. But there's something more insidious. So this is a fix for call by name, but what about for call by value, right? What about for call by value? So in this case, because it happens that this is a terminating language, we've got that termination property that everything will result in a value. You don't see this extra difference, but for now, with recursion or with fixed points, like PC plus polymorphism, I do at some point. What happens then? So, something. So if we look at, this is call by name. If we look at call by value, what happens? Remember, if I've got recursion, I could have that omega thing that reduces to itself, right? So I've got omega, which reduces to omega and spins on forever, right? So that's something I've got. So what if I have lambda x dot, or of type alpha, and I don't really care what's there, and I apply it to big lambda beta of omega. What happens there? Right? So if I erase this, so erase of this thing is equal to lambda x dot 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 applied to omega. Right? So what do I do here in call by value? I evaluate the function, which is a value, so I'm done. Then I evaluate the argument, which again is a value because there's a big lambda there, and those are values, so I'm done again, and then I plug it in, and I go. What happens here? And if I don't use x, it's just away. And it never used parameter that I could have deleted. But here, evaluate the function, it is a value, and I'm done. Evaluate omega, that's not a value, will it ever be done? No, so this program does something different than here. Let's suppose here I just return 9 as my result. This is a program that will return as its result, this is a program that will loop forever and never return anything. So this is like a worse problem. I'm only looking at numbers, surely that's safe, and yet erasure messed up my program, right? It changed the meaning of my program. So this is the really annoying problem. The first one is fine because you normally don't want to do that anyway, but this is really annoying. And it says that erasure is wrong for call by value. So even though the types don't mean anything really for, at least the type specializations don't mean anything for dynamics, it's just bookkeeping noise, big lambdas kind of do when I'm in call by value because there's a difference between things that I'm willing to substitute and things that I evaluate first. And that's a coercion between the two. So does that mean you can't type erase call by value programs? Put that another way, does OCaml have to keep types around because of this really stupid problem? So you might guess no, because OCaml doesn't keep types around, or SML, or many of these other languages. Or at least this isn't the reason why they have to, if they do. And why is that? Well, in terms of running a program, I don't really care what this alpha is. That's going to be ignored. I just kind of care that there is a lambda here. Just like this coercion of, you don't need to evaluate me now, just when you actually use me. And so here's the trick on how to do erasure for call by value. A little bit maybe confusing the first time you see it, but the idea is fine. I need type abstraction and type instantiation for the reasons of knowing when to evaluate something and when not to. But it doesn't matter what I put there because it's ignored, or it doesn't impact the behavior of the program. So what you do, this part is the part to do with Lambda-Calculus. But when you've got a big lambda, you don't really need a type sort of thing there. I could just say lambda x dot erase e where, let's make more room, where, x is not used. It's just some dummy variable, it doesn't matter. In the free variables of e, exactly, right? I just need a dummy variable. I just need a stupid lambda to tell me that there was a generic thing here. And then, so when I see this, I just need to apply it to some, let's say, dummy unit argument. It doesn't really matter what it is. And you'll see this in some paper or other study that's doing polymorphism and type erasure. You'll kind of see this trace of polymorphism in the program, but not in a useful way if it's done like this. That's really common. And if you have this now, the problem goes away because, where did it go? Here it is, right? I don't do this anymore, right? The erasure of that is lambda x dot omega, and I do the same thing either way, right? I still have this delay involved that I don't need to evaluate the argument. Okay, yeah, so that's type erasure. So the fix for call by value is, you actually don't need that fix anymore because you'll still have the big lambda just becomes a useless little lambda. It's only there for delaying reasons, but you have to change what type erasure means to remember where instantiation and polymorphism happened in your program, right? It's the kind of shadow tracing. And this is like kind of a thing that happens. There is this interesting interaction between call by value and generics. It's the same thing in standard ML, which is where I think the first time that kind of came up, which is called the value restriction, where the idea is in ML, if you write a function, then it's generic when possible. So if you say let val id equal, or id of x, I guess the id is fun, x goes to x, so this is a function, the identity function, right? So if I've got that, then this will have the type, right? That will have the type alpha to alpha for all alpha. And that's okay because that's a value. If this were something that's not a value, you wouldn't get something specific. And there's a similar kind of, you can come up with counterexamples to type safety involving effects like references, right? We haven't talked about what happens if I have references in mutable state, but there's all these kinds of interactions with generics. So this is the easy version, but the lesson is, you kind of want these type erasure-y things, and even here we don't say for all at all in the first place, but you do have to think how types are connected to the semantics of how you run programs, even if they don't tell you how to decide the runtime. There is a connection. Okay, so we're at 3 now, so I think that's what I've got. I can answer a few questions, and then we can move on to finish off today's lesson. So Jan will finish off by talking about how to use System F to encode a bunch of more useful types, where kind of the story there is if you're stranded on a desert island and you can only bring 2 types with you, which ones will you bring, right? So that's the idea there. So question?
What about type classes?
Type classes are a kind of different sort of thing, so it's still, I think the question is like how it interacts with for-alls, maybe. So a type class is a constraint on a type variable. So you can say something like, sort is a function that, takes a list of A's and returns a list of A's for any A's, but only the ones that I know how to compare for order. Because if I can't compare 2 things for order, how could I sort it? Right? So it's a for all plus a restriction. And so it does fit nicely in with this story of polymorphism. So that's a little bit different than a type case, which says I will implement sort completely differently depending on what the type is. It says the implementation is really exactly the same modulo what comparison means. So that works pretty well. Just in your type language, you would have constraints, or you could bake it into the for all. When you quantify over something, you could say, for all alpha satisfying such and such constraints, right? So that's kind of that is baked in there. Yeah. Yeah.
What's the existential type?
The existential type, so I didn't have time to go through that, but it's the other type quantifier and the use. So here it's all about, I want to define one thing and use it also at all sorts of types. The existential type is more about abstract data types. So the idea there is something like, I want to define a signature for what a set of numbers are. Right? And so what's a set of numbers? Well, there's some type that represents what it is, and there's some operations on it. Like, I have the singleton set of one number. I can union them. I can ask if something's in that set. But a client which uses this thing, right, if we really want to just say, I can work with any implementation at all, it shouldn't really depend on what that representation is. Right? The implementer of sets needs to look into them to figure out what to do, but the user just uses those operations. And so whereas polymorphism, the for all, is essentially hiding the it's hiding the type from the definition of the thing, right? So the identity type doesn't get to see what alpha is, so that constrains what you can do with it. And the client or the user, whoever imports your polymorphic function, gets to pick whatever the heck they want. Existentials are the other way around. The implementer gets to pick whatever the heck they want. And now it's the user library that has to be constrained so that they can't leak out representational details and say, aha, I knew you were using a list of numbers to represent your set of numbers, and therefore I'll do weird stuff. And so that's the difference. Right? So hiding the types from the user rather than the producer. Whereas here, this is hiding types from the producer, and the user can do anything they want. So it's who's liberated and who has to be type blind. Yeah. Okay. Yeah.
Well, lambda is a type of big lambda is a type of binder. For all is a type of binder.
Yeah.
View is a binder.
Yep.
So is that
there's lots of binders. All binders have alpha equivalents. I don't know if that was the question, but
yeah, something like that.
yeah. So case for sums also have binders in them. Remember? And also the recursor for numbers have binders in them. So programming languages in this kind of case, in this representation, have tons and tons of binders all over the place, which is kind of why that issue of binding and substitution and alpha, while it's essential, is absolutely tedious, because they appear all over the place, and you have to keep saying, yes, they are binders, yes, this is static substitution. But yeah, so there's lots of binders, and we didn't formalize what those mean completely in general in these lectures. We kind of did some examples and then said, yes, it works the same. If you're really interested in that first section of PFPL, Programming Foundations, or Practical Foundations for Programming Languages, has this general theory of what if trees had binders in them? How does that work in general, regardless of what the tree is? So that's kind of like a, can you solve this problem once and for all? It's a little bit more difficult to work with those directly, but you can kind of like get the idea after one or two examples, and then you say, yes, yes, of course, that's how it is, right? But that's lots of binders running around. Yeah. All right, so I think I'll stop there. If there's, well, I guess one more question, and then I'll stop.
Does the restriction apply to some expression recursively?
No, just the final one. Yeah, for this, I think, yeah, just the overall type. What's the type of the expression I'm evaluating? You can have for alls inside of it, just not the top level thing. Kind of like, well, many programs, right? It's kind of, well, you run them and you get back yes or no, or a number. You can use functions and strings and arrays and all sorts of stuff inside of it. But the final thing you see is just like a number. That's kind of the idea here. It doesn't matter how many for alls you use in it, as long as you're not running a for all as the final type. Yeah. All right, so I'll end there and then pass it over to Jan.